Okay, so today's lecture is on Facebook's photo management processes, and we'll make a good dent in this, probably something like halfway through. All right, so the big things we're going to talk about: system scale, we'll mention big data, mention capacity issues, we'll talk about different types of memory, and finally, we'll talk a little bit, we'll just mention Facebook's haystack system. Next week, we'll talk in a little bit more detail about object storage systems, databases, that sort of thing. All right. So first thing, the durability of Facebook. Let's see, this screen is misaligned a little bit, but I guess we're showing, okay, this is good. So Facebook is really big, right? And the fact that it's really big gives it a lot of inertia as its kind of social media, right? Basically, people stay on because their friends are on. Now, it's getting to the point where a lot of people are not joining Facebook, but the people that are still on there, they're probably going to stay on till the very end. Other thing is because the rate of internet adoption has slowed down a lot relative to 20 years ago. It's really hard for any new competitor to break into Facebook's model for social media. All right, so we're going to drop out for a second, and I'm going to show about this in versus MySpace. All right, just because this is something that doesn't go away. This is one of those economies of scale type things. It's an indirect effect, though. So down here, I'll put down the year. Let's do 2004, 2014, 2024. Okay. And Facebook size in 2004, Facebook was just getting off the ground, right? It was just tiny. And MySpace was substantially bigger, right? So we'll draw MySpace. Well, we'll do that light green. That's kind of close to their color, if I recall. Okay. MySpace was more, oh shit, was more like this. They were big, right? But the whole social media was just kind of in its infancy then. And so the whole pool of total people, right, was more like, I'll do purple, was more like this. That meant, right, Facebook, I'll just do the bar here of all the people. Facebook had a pretty easy shot. If it had a better app than MySpace, a better experience, there were a lot of uncommitted people who might feasibly join in. They might say, oh yeah, okay, it's time for me to join social media, which one am I going to join? I've heard good things about Facebook. I've tried MySpace. It kind of sucks. All right, I'll stay with Facebook. So by 2014, right, the pool of internet people was like this. Facebook's share was something, Facebook share was something, let's say, close to this. And MySpace, was basically a stub. There are still MySpace accounts. I believe Fox bought it for like close to an absurd amount of money, close to $1 billion back in the late aughts, like 2008 or something. And I think they sold it basically for $1 to Justin Timberlake about 10 years later. Well, I don't track these things that closely. Anyway, so that's about what the situation is there. Now, at this point, if some new medium comes along, even if they're better than Facebook, right, they first of all have to convince a lot of these undecideds. If it's 2014 and they haven't joined social media by then, there's a pretty good chance that, they're pretty iffy on the whole thing. But even so, to get bigger than Facebook, they have to capture basically all of these uncommitted people, reluctant people, and take some market share from Facebook. Plus, Facebook has, a long lead and a lot of assets. It's really hard for that sort of thing to happen, right? So that's, in 2024, Facebook's even more entrenched. Although these days, a lot of people have multiple accounts. They might have not only Facebook, but also Instagram and Discord and whatever else is out there. Again, I don't track the new apps too closely, but, and of course, Twitter. But Twitter is qualitatively different. I mean, Discord is too. All right, so Facebook is a little bit bigger market share, maybe more like this at this point. Okay, so it's really tough for anybody to dig in and kick Facebook out at what Facebook does, right? But that's not the whole story. The story is there's a bunch of issues that might lead people to ditching Facebook entirely, right? Things like privacy issues. There were, after the 2016 election, there was a lot of concern that Facebook was selling people's data. Any big security failure, people might opt out of Facebook for that. Any sort of large scale system performance failures, right? Really slow page loads. Facebook's probably keeping on top of that. I wouldn't worry about that too much. I would say privacy, maybe security are the bigger concerns. People might leave in large numbers. But the biggest risk is people might tire of social media generally. They might say, Facebook, it's kind of toxic. I really don't like a lot of the interactions I have with people. And this is something that historically happened. It maybe peaked 5 or 10 years ago. It's hard to pin it down exactly, but Facebook at one point, their model for showing you your feed was essentially that if it's content of the kind that you've interacted with previously, we're going to show you more of it. But the problem is a lot of the interactions that happen on Facebook were argumentative. People would get into heated discussions about various topics, politics, religion, what have you. And, just because Facebook kept serving them up those conversations because it had a history of interaction didn't mean that people were having fun. So eventually what happens is some of those people just, bailed on it. They stop using Facebook very much. They go off to other things, or they never joined Facebook in the first place for whatever reason. So Facebook does have concerns, but for, the time being, Facebook looks like it's still making bags and bags of money. Okay. Also, a few years back, they had remember that metaverse? Remember the fail with that? The sad little, yeah. In case you didn't, in case some of you are not aware, right? Facebook made this thing that's basically like, a creative mode in Fortnite, but a really shitty one. Okay. And you were just like heads floating around. Anyway, if you're not aware of this, I mean, that's literally what it looked like in 2020. That was the first image that came out that they were showing people. And it's like, oh my gosh, if they think they're going to be competitive with that, that's just kind of sad. All right. Anyway, so yeah, so Facebook has its problems, but for now, as social media, yeah, it's still the top of what it does. But they need to be continuously innovating, trying new stuff, because again, the main revenue stream from ordinary users my age is obviously kind of drying up. So part of that was acquiring Instagram. There have been other things in the works. Okay. Anyway, when we talk about scale, we just mean bigness. So Facebook is super, super big, close to 3 billion monthly users, 2 billion daily users. And let's assume for the purposes of discussion that all of those are actual individual humans, right? It's a lot of people. It's a very large share of the world's population. Even if only half of them are real humans, that's pretty big. As last number I had, hundreds of millions of photos uploaded daily. That was from 2013 as the last concrete number I could find that said something like 350 million photos uploaded every day. It's probably comparable. The number of daily users is kind of flattened out. So I don't know, maybe it's a little higher, a little lower, but probably same in the ballpark. And last year's annual revenues, $135 billion. So it is a very big operation. And when you have a big operation, things that are simple on a small scale, simple to design or manage, really require massive specialized systems for Facebook. So, for example, does anybody know how many rows, the max number of rows you can have in an Excel worksheet? Anybody want to hazard a guess? No? Last I checked, it was about 1 million. Okay, so you could have 1 million rows in an Excel worksheet. Now, if Facebook wants to use off-the-shelf Excel to manage its 3 billion accounts, that's not going to work very well, is it? Right? Aside from anything about how fast the application is going to run, it's just the fact that they're going to have to put data in 3,000 different worksheets to do anything with all those users. So that alone, they're going to require some kind of specialized new software to make do with that, right? Ordinary Excel isn't going to work. And then think about finding files, right? Imagine you have an old laptop, you've had it for a few years. There's a lot of files on it, maybe around the order of 1 million different files if it's a Windows machine. And if you want to just search the whole hard drive to find a particular file, Yeah, you can go in somewhere and the wheels will spin around for a while and it'll eventually find it, but it takes a little while. Maybe it takes a long while. But think about Facebook. They have hundreds of millions of photos uploaded every day, right? Which in practice, what does that mean? Multiply it by 1,000. Every 3 years, they have hundreds of billions of photos. So they literally have trillions of photos, we can reasonably guess, and then you're asking somebody to find a few of them quickly so that when you go into Facebook, it can construct your feed and throw a bunch of stuff at you, right? So the mechanism that you have there for looking for files on your laptop, it's got to be a lot different, a lot faster, a lot more organized on Facebook. Okay, so scale, while it brings opportunities, we've talked about economies of scale and how it can be very good, it also brings in severe big problems that need to be solved. Okay. All right. So numbers you should all be aware of because I'm going to talk about these now and then throughout the course of the semester, right? These are the three that you're probably very familiar with, right? Once upon a time, a kilobyte was an important unit, but now it's like a rounding error for things. But you guys should know kilo, as in kilogram, kilometer, just means 1,000, right? So a kilobyte is a short text file. If you say maybe every text character occupies 2 bytes of memory, then, 500 characters. So like maybe a single page in big handwriting. Megabyte, maybe a reasonably big image. If you assume 4 bytes per pixel, right, standard 24-bit color with transparency, then you're talking about 500 pixels by 500 pixels. Not huge, but not nothing. Is that right? I think it is. Okay. Gigabyte, a billion. Okay. So what's an example of a gigabyte of data? Long video file. Back in the day, CDs could hold 665 megs of data. And when they came out with DVDs, they held twice as much. They could hold 1.3 gigabytes. So if you can pack a movie on a DVD with some director's cut and extra interviews and stuff, yeah, long feature film, about a gigabyte of data. Terabytes, well, typical hard drive now, right? Most machines, you get options for 1, 2, 4 terabyte hard drives. So rough idea, that's what those things are. Now a petabyte is something that we as individuals generally don't have to worry about, but organizations do. And an organization can very easily gather a petabyte of data just through supply chain operations, right? So for example, if your supply chain, if at every point along the trip, you're gathering data like every minute about where the truck is and how fast it's going, whether it's stopped or moving, things like that, any trip could gradually gather quite a bit of data. And if you have many trucks doing many trips, like Amazon does, a petabyte is going to add up pretty fast. So a terabyte, typical hard drive, petabyte, you could think of it as a truckload of hard drives, like 1,000 hard drives worth of data, or, rough numbers, 1 day's new Facebook data. If you make some assumptions about how big the photos are, then the raw data being uploaded to Facebook as photos is around the order of a petabyte. An exabyte is 1,000 petabytes, or roughly 3 years worth of Facebook uploads, or if you want to look at it another way, 1 million full hard drives. Okay, so that's a lot of data. And if you're talking exabytes, that's around the range of all data of a large business. Now, the really big ones, Amazon, Facebook, YouTube, whatever, they're going to have more data. Google, they're going to have more data than that. They're going to have many exabytes of data. Are they going to crack 100 exabytes? Maybe. I'm guessing they're probably mostly still in double digits, but, maybe not. They probably keep data on a lot of stuff, so maybe they've cracked that. But an exabyte is a very, very large amount of data. And finally, zettabytes. A zettabyte is a significant fraction of total annual internet traffic, right? These days, the volume of total worldwide internet traffic, about 10 zettabytes. So zettabyte is a very, very, very big amount of data. Okay, but the big ones to worry about are this range. Basically these are individuals, right? Individual files. This is like hard drive. And these are like anywhere from medium organization to big organizations dealing with that kind of data. All right. Okay. Next thing is big data. So big data is a term you might hear, but these days you mostly hear it as something that people don't say anymore, as a concept that's outdated. But the idea with big data is that if you as an organization started having to deal with data in volumes that made using off-the-shelf tools impractical, you would say, gosh, we have a big data problem, right? And these big data problems can happen in a variety of ways. One of them is simply the volume of data. And we as ordinary people, we can have this happen. On occasion, you could have your hard drive get full, right? Depending on what you're doing. I remember a couple years ago, there was a Guardians of the Galaxy game that all by itself had like a 250 gig footprint on your hard drive, right? I have Fortnite. I don't know the exact number, but it's somewhere in the range of 100 to 200 gigs on my hard drive. So you get a few of those things, they're going to add up pretty quick, right? And you're going to need a second machine, or you're going to need to uninstall and reinstall other things if you want to do anything with it. And that's a kind of big data problem. Very simple one, though, in terms of volume. Imagine if you're a business that has a list of customers. And, day one, you're fine. You have your customers. You keep them all on one machine, right? You keep them all in one file. Suddenly, as your business gets bigger, it starts being a problem to store all that data in a single file or in a single Excel worksheet or in a single easily managed unit, whatever that may be. And you have to break it up under multiple applications or multiple pieces of hardware. That's your basic volume problem. Velocity means how fast data is arriving, right? So imagine you're running a transaction processing system, and every transaction needs to wait on other outside organizations to kind of do their thing, right? You have to send an information bundle out to Visa, tell them here's who's buying what and how much it costs, and Visa has to process it, send the results back. I guarantee you there were some velocity problems when Amazon started really spiking up and sending a lot of credit card traffic very quickly to these credit card companies. They had to start jumping to keep up with it. Variety. There are some problems holding different kinds of data. So one of the ones that we'll talk about later in this lecture, not today, but next week, is that if you have video data or image data, and some of the files are very big and some of the files are very small, that creates a need for different database structures to handle them. And last one, veracity. What's veracity? What does that mean? Who speaks Spanish or took Latin, or what's veracity? Nobody? Yeah. Yeah, it's like accuracy, right? Veracity literally means, having truth, right? Being true. So veracity means, is your information accurate? And you can see this, just imagine if you have two hard drives very full of copies of the same data, right? You have one massive amount of data and you have other backups throughout the organization. Checking whether the backups are accurate, that's going to be a lot more work the more data you have. Okay, so all of these kind of problems, they're known as the 4 Vs. You may see some cases in other courses or other texts or other whatever where they talk about the 5 Vs. They throw in an extra one, but these are the kind of issues that happen when you have a lot of data. Okay. Now, reason why you shouldn't use big data as a term is it's inherently imprecise, right? So big data, you have an idea that, whatever situation you have is too much to handle with basic gear. But the kinds of problems and the kinds of solutions, they're going to be different depending. So, for example, what UIC might perceive as a big data problem is going to be trivial to Facebook. They're going to say, oh yeah, we were dealing with that back in 2006. Likewise, what was a big data problem in 2000 is pretty trivial for 2025. For example, in the late 90s, I moved to Chicago, bought my first desktop. I'd been a laptop guy before that, bought my first desktop, and it came with a colossal 6 gig hard drive. I was like, 6 gigs, what am I going to do with this? And I put some stuff on there, but even though I had that desktop for like 5 years, I only ever filled the hard drive like half full. When I scrapped it, there was still like 3 gigs of space on the hard drive. Now, right? 6 gigs, that's nothing. 3 gigs, like even a very low-end machine has 3 gigs of RAM. So yeah, none of these problems that I experienced back then would be an issue right now. Okay, so that's what there is to say about big data. Questions, thoughts, experiences? Anybody heard about Elon Musk cheating at online games, sort of? No? Apparently, in multiple games, some of which I'm lightly familiar with. I mean, I haven't played, wasn't Dark Souls. What's the sandbox one that's based on Dark Souls? Elden Ring. Elden Ring. Apparently, he had, like, on that one and some others, that he had gotten somebody to grind for him for, like, who knows how long, and then just showed up at the end to beat the bosses, and then said, "Oh yeah, here I am. I'm one of the top guys in the world." And he's apparently done that on multiple games. And so the question is, either one, it's sad that the guy who's, the richest guy in the world still feels like he needs to pretend like he's a teenager who's the best in the world at video games, or else what else? Or I guess that he's taken that much time away from his company. But I don't know. I don't know the truth of it. I just read something about it today, so I thought people might have heard. Anyway. All right. Well, anyway, capacity problems then. So imagine you're uploading a photo to Facebook, right? There's a few things that have to happen. First of all, Facebook has to actually accept the upload, has to run some kind of scan on it to see if there's any prohibited content, has to make backup copies of the image, right? So it stores the original and then makes the backups, and then distributes it to other people through their feeds. As soon as somebody uploads something, it can be available to the person's friends, right? And being able to do all those things quickly at scale is really important for Facebook, right? Because it has billions of users. So Facebook's got to do these things reasonably quickly, right? And do that in real time so that people are, they feel better about their Facebook experience. So basically what happens, Facebook has to match supply and demand for photo uploads. So in terms of demand for that service, we're talking about how many photos all of Facebook's users at any moment in time want to upload. And to an extent, you can influence that, but Facebook can't control it. Facebook doesn't want people to show up, try to upload something, and Facebook pops up a sad face and says, "Sorry, we're really busy right now. Please try again in a few minutes," right? Nobody wants to see that. Other kinds of things like throttling or doing other limitations. Again, if Facebook isn't doing this fast, that's going to leave a vulnerability for competitors maybe, right? People say, "Oh, Facebook isn't as good, takes forever to upload photos." So the supply then is Facebook's ability to process those. That's going to depend on the hardware that's available and the process design. So for example, right, go back to this. If Facebook does a super detailed check, right, that could take a very long time. If Facebook does a quick check, that'll be a lot faster. If Facebook does things like say, "Oh, this person has a history of, not posting anything especially controversial, maybe we give him the light check," right? Other people, they give a more in-depth check, whatever. Okay. But however the process is designed and whatever hardware is used, right, at some point, the process is as good as it's going to be, and increasing the capacity is simply going to require more hardware. So there's this kind of problem. Now, we're going to do this in a little bit of math. This is as mathy as the course gets, so don't panic. We're going to do this. Okay. I'm going to copy that over to Paint. Oop. There we go. Okay. So this is the equation that we're doing. And I'm going to copy, I guess I'll copy all the little components, just so you understand what we're talking about here. It's a little hard to move some of these things. Okay. So this first one, this is a lambda. Oh, I want underline. I don't even want bold. lambda, which is a Greek L, I'll be OCD and capitalize it. Okay, which signifies the arrival rate, right? Basically the rate at which events happen. Okay, so the bigger lambda is, the more things are going. So in this case, we're talking about photo uploads. So lambda is the number of photo uploads per second. Okay. S is the number of system processors. Basically, the units of hardware available to do the task, right? So basically, if you multiply S by some number, that's how much you're increasing capacity by. If you have, twice as many system processors, you can process twice as many events per second, okay? And the last one is T sub P. T sub P is the time per process. Time required to process each task, right? So likewise, if the time goes down, if T sub P gets smaller, then this side of the equation, so T sub P gets smaller, you're dividing S by a smaller number, so you effectively gain more capacity, right? Reducing the time by a factor of 10 is the same as increasing the available resources by a factor of 10. So this is your basic problem. And again, there's only so much you can do with this. If, demand is what it is, right? That's the arrival rate. That's what people want to do. And in order to keep up with that, you can either increase the number of system processors, hardware costs money, or you can come up with a better, faster process, okay? Obviously, which would you rather do? Add more hardware or come up with a better process? Better process, right? What you would want to do. Okay. So if the upload rate increases, what happens is either number one, you got to add more system processors, or you have to shorten the processing time, or else there's going to be a backlog, right? You don't have enough capacity to process all these tasks, and people have to wait and they get unhappy. Okay. Now, Facebook's solution to managing all of this is they have a massive system combining RAM and permanent storage, right? So you guys are surely aware that in general, RAM is a lot faster than permanent storage. And they do what's called caching in RAM. Caching basically means just putting stuff where it's easier to get to. So rather than storing data on disk, it gets stored in RAM so you can get to it quickly. And they also make multiple copies of it. We'll talk a little bit more detail about this kind of system. So for photos, the system is called Haystack. And the logic behind it is, finding a single photo in this massive repository of photos is actually a worse problem than finding a needle in a haystack. So before we get to really understand Facebook's solution, we're going to talk more about different kinds of memory and different kinds of databases, right? So we'll get to some of that. So today, we'll probably finish up talking about memory. All right. So the first issue with memory is whether it's changeable or not, whether you can write to it. So the process of changing the contents of memory is called writing. Writable memory is memory that you can change, okay? Some kinds of memory you can't change, right? So here, read-only ones like ROM literally stands for read-only memory. Ordinary people, ordinary users can't change the contents, right? Other kinds, read and write, there could be volatile or non-volatile. Volatile means the contents go away when the power goes away. Non-volatile means it's permanent. So again, hard disks or flash memory, right? You can have a hard disk on your computer. If you don't use it for a long, long time, you turn your computer back on, stuff is still in there. Likewise, flash memory, whether it's solid state drives or a USB drive in your pocket, again, you can leave that without power for a long time. Memory doesn't go away. Ordinary RAM in your computer though, right? We've all experienced a thing where we had a power outage or the battery failed or something, and boom, you just, whatever's in RAM, you lose. You don't keep, because it needs power to keep it going. Okay, so those are your two basic types. Now, different kinds of memory that are out there: sequential access, direct access, random access. So the first memory that was out there was what was called sequential access memory. And basically, with sequential access, it's like an old-timey cassette tape, or if you're watching something on Netflix, you got to fast forward or rewind to get to the point of the memory where you want to read. Now, again, once upon a time, sequential access memory was pretty common because it was cheap. But these days, it's used in such small quantities that, the manufacturers don't gain economies of scale anymore. So it still exists. Like they have some tape drives for extreme conditions that are still available these days, but they're pretty expensive. But even like through the mid 90s, you could buy like a 1 gigabyte tape drive for a fraction of what, like a 50 meg hard drive would cost. So, 30 years ago, sequential access memory was pretty slow, but it was also very cheap. Next one is direct access storage devices. So easiest way to think about that is old-timey vinyl records, right? So with vinyl records, there are going to be different tracks, like each track is a song, right? And if you want to move the needle to play a particular song, you can bring it to the start of the track, but it's really hard to precisely target that needle to arrive somewhere in the middle of a track, right? And this is what's going on some of your old-timey discs, right? Basically, the drive head, the part that reads it, moves to the start of the track and scans the length of the track. If anybody out there is still using CDs and DVDs, they use a similar technology, right? But a lot of these, you don't see that much anymore. The big one, of course, random access memory. Random access memory was a big jump forward when it was first introduced because data could be accessed in about the same time, regardless of the memory address where the contents were. That's why it's called random access, because for these two models, sequential access was far faster than accessing memory addresses in random locations. Random access memory, it was about the same. So much faster retrieval than disk drives generally, but also a lot more expensive. Although there are some specialized types of disk, solid state drives, that are comparable, even faster than some RAM, but those things are super expensive. So there's no longer like a one single answer. Wasn't that long ago that it was just, yup, RAM is a lot faster than disk. Now it's a little murkier. Okay. Of course, where you see it, main memory on your computer, some USB storage and solid state drives are also going to be RAM. Okay. Now, your basic non-volatile memory, right? Obviously, one of them is read-only memory. If the memory instructions, the contents are, physically burned into the chip somehow, of course, you're not going to be able to change it. Other things, like if you actually burn a DVD as opposed to simply doing it magnetically, if you use a laser to etch the surface of it, again, that's effectively read-only memory. And there are some kinds of writable non-volatile memory, right? Of course, disk. Flash memory, for typical flash memory, is going to be pretty slow for doing computations, so you wouldn't want to run apps with it, but it's fast enough for storage and retrieval. So you can use it like a disk drive. Again, NVRAM, non-volatile RAM, similar stuff. It's pretty fast, but it can also be very expensive. And the biggest issue with all of these is that these kinds of flash memory, they wear out over time. Depending on whether it's low end or high end, that might wear out after a few hundred read and write cycles. It might last a lot longer than that, but still, eventually it's going to wear out, and you don't want to use it for ordinary application running because of that. Okay. Now, what we think of as, ordinary RAM, those other things, some of them are in fact random access memory. But when we think of ordinary RAM, it's, what's there in our computers. And the first ones were, there was a split between static and dynamic RAM. So dynamic RAM was introduced in the 70s. It was widely used until the 90s. And it was eventually replaced by what's called synchronous RAM. So dynamic RAM is one of those things. Back in the day, we were glad we had it, but it's obsolete now. And like all these other RAM types, the memory contents are going to be lost immediately as soon as power goes away. Basically, the voltage coming into the memory is what holds the switches in place, and when the voltage go away, the switches drop down to zero. Synchronous RAM, on the other hand, Synchronous RAM, there's an external clock. I'll explain very briefly how that works, just because, if anybody's wondering, this is for learning purposes only. All right. So suppose you have a unit of memory, right? 1 byte of RAM. 1 byte of RAM. There are basically going to be 8 signals going into that. And for every signal that comes in, there's going to be a little window where the system is not sure whether, the signal is complete. So I drew 8 lines because a byte is 8 bits, 8 1 or 0 values. So in every unit of time, there's either going to be a signal coming in on the wire or not coming in on the wire. Okay. Now with the external clock, what they can do is this. They can say, okay, we're going to designate some time interval where it starts and stops. Okay, so if there's a signal that starts between this time and that time, and you read it, that's when you know that that was valid for that particular communication going to that byte of RAM. And basically, the shorter interval that happens, right, you can fit in more and more signals per unit time. And so synchronized RAM, what it does is it controls the length of that interval. There's an external clock associated with the RAM. It says, okay, here's time 0, here's time end of this period. Either you got a signal on this line or you didn't. Okay. Now, all the different generations of RAM are known as DDRs. DDR stands for double data rate. So every new generation of RAM, like going lately from a DDR4 to DDR5, DDR5 is about twice as fast. DDR6 is going to be, which for all I know might have just been released. I know it's pretty imminent if it hasn't been. DDR6 is going to be twice as fast as DDR5 and so on. Okay, so that's what synchronous RAM is. And if nothing else, now when you're out shopping for computers, you'll know that DDR5 is twice as fast as DDR4. So it's maybe worth the extra money. Okay. Last kind is static RAM. So static RAM is neat. It's a different kind of structure than ordinary RAM. In general, it's faster and consumes less power. Thus, it doesn't heat up as much, doesn't require as much cooling relative to synchronous RAM. But the weird thing about static RAM is that physically it occupies more space. It's bulkier. And so static RAM, even though it's really fast, if it starts getting too big, that block of RAM is going to lose the time advantages because the electrons have to travel through longer paths and they lose the advantage that way. So static RAM is the kind of RAM that's done as a cache attached to the CPU. And so if you're out shopping for machines and it says, oh, it has a 256 megabyte L2 cache, that's static RAM there. It's a little bit of memory attached to the CPU and it's super, super, super fast, but it's only used in small amounts because if it gets too big, it gets slow. Okay. So that's it. That's basically the different types of memory. Any questions on any of that? Normally I would do some let's do it. Let's do for fun. Let's do a question in iClicker. Oh, I never started the session, did I? Oh, well, that's okay. We don't take attendance too seriously early on, but I'll start the iClicker session. That's firing up. I'm going to bring these over. There we have iClicker. Good. Let's start. All right. So these are all old actual exam questions. Oh, good. We have it. So I'm going to do let's figure out what question I'm going to ask first. And then I'll launch it as a poll. Ah, good. This will be a good one. All right. So we'll do number 5 since we just talked about it. Okay. Number 5. And okay. So now you should see on your iClicker, you should see that you're being asked a multiple choice question, and we'll get in the results. I'll kick back and wait like a minute. I'll give you a minute to respond. I'll give you another 10 seconds or so. Don't panic if you haven't been able to load it in time. This one is not that serious, but all right. We just want to move on with things here. All right. I'm going to stop it. Ding, ding, ding. All right. Look at all those people rolling in. Okay. Cool. So, what's the right answer? Most suitable for quickly performing a large series of simple mathematical computations. Well, it might be NVRAM at this point, but this is an old exam. So back in those days, NVRAM was probably something you didn't want to use. And you still might not want to just in terms of expense. Correct answer would have been static RAM. So let's see. Yeah, pretty good. Good job. All right. But yeah, you could make a case for NVRAM. You wouldn't want to use dynamic RAM because that shit was old even in the 90s, right? Direct access storage devices, sequential access memory. If there are a large series of mathematical computations, right, you're going to end up having to bounce around, store the results somewhere. It's going to be a mess if you use either of those two modes. All right. But not many people did that. And they might have just clicked the wrong thing anyway. All right. Cool. Okay. Well, the next thing we'll talk about RAID devices. I don't know. We might close. We'll talk a little bit more after, but not much more. Okay. So the idea with a RAID device is it's a set of disks within a single application housing. Okay. And RAID devices, they still exist, but the best reason to discuss them at this point in time is that it's conceptually similar to the cloud. It's like a little bit more concrete version of what's going on in the cloud. So it's basically within one single storage device, you have a set of separate hard disks, and there's one single interface that all the communications go through. So as far as the user is concerned, they just send instructions to the disk, and the disk manages it and gives the results back. Okay. And there are different RAID models that can allow emphasizing write speed or read speed or reliability. So this is the thing. If you have some sort of operational concern that it's really important that your system writes data quickly, then you could set it up one way. If it's really important that your system reads data quickly, well, you could set it up a different way. And if it's really, really important that you never lose any memory, then you could set it up another way. Okay. And you can mix and match with some of those as well. So we'll talk about that. The three basic techniques are striping, mirroring, and parity. We'll talk about those. So here we have a disk, a RAID device, and I'm going to draw a disk. I'll do, I guess, close enough. And then sure, we'll just do it all. Whoa. Okay, good enough. Okay, so we're going to put 3 disks inside this RAID device. And here is the interface. That's what everything connects to. Okay, and so this goes to dot dot to user. Okay, so this is our RAID device. Now, the first technique is striping. So striping, let's do that in, we'll do it in red. Okay, striping means breaking a file into segments and storing each segment on a separate disk. This makes input-output, well, say read, write operations faster, right? So in this case, the bottleneck for speed with these devices is simply that the individual disks take a certain amount of time to do whatever they're doing. The network aspect of it on the same device is going to be like a rounding error, because this isn't going over the internet. This is going over with a direct connection to your machine. So if you have a big file, and instead of having to copy the whole thing to each disk, you only copy a section of it to each disk, it's going to go a lot faster. Same thing for reading from the disk. It's going to go a lot faster because each disk only has to, spin around as third as far. Okay. Second one is mirroring. Mirroring means making a copy of any file on multiple disks. Okay. This will increase reliability, right? Because you have backup copies automatically, but also requires extra work. So if the system is kind of busy, there might be delays, right? Obviously, if all you're doing is uploading writing a file to disk at very long intervals, then yeah, the fact that you're doing it on multiple disks isn't going to be a problem. But if they're a big file, and while that big file is being processed separately on each disk, and there are other actions that have to wait for that to be done before they can do their thing, right? If the system is busy, that's going to cause some delays. But it does increase reliability because if one disk breaks down, you have the other two copies, okay? And read speed is not affected because basically for reading a disk, even if there's mirroring, you just pick one disk at random that might have it and you read it from there. So the time for reading is going to be the same. But writing takes extra time. The last one is parity. And parity is confusing. So parity basically means here having the ability to identify errors in stored memory. Okay? And the way it's done is by encoding additional data with each portion of the file, right? So done by encoding additional data with the file. But this means even small changes to the file necessitate redoing the parity data, which can be very slow, right? So if you don't have parity, you make one small change to a file on a disk, like you edit one character in a Word document, right? That's not going to be a big change. But with parity, you have extra data embedded throughout the file, and you have to look at that. Maybe you have to look at the entire file to see what the new parity value is going to be, or you have different segments where there are parity values embedded. You're going to have to do a lot of extra work anytime you're changing something. So parity is especially good if the data in the file never change. Now, let's talk about this a minute. So this is just general concept here. We're going to draw a picture. I'm going to draw a picture. Okay. So this is my patented beach picture. Move that down a bit. Okay, boom. And we have the sun. Oh, come on, you can do it. Give me a circle. And one last thing we need at the beach, we need a starfish, of course. Okay, so this is us at the beach. Nice. Now, suppose I have two copies of this. And suppose that in this one, there is a purple dot there on the beach, right? It doesn't look very big there, but it's there. Okay. I'll make it a little bigger. Okay. How would we know as individuals which of these is the correct image? So one is the original, one is the backup. That's all we have, right? We don't have like a master copy as such, because maybe this was the original and this was the backup. One of these two has an error that somehow happened. How would we identify which one is the true copy? If you're looking at this problem, you're thinking, shit, I don't know. Well, yeah, that's the problem, right? The problem is you don't know. There's no way for the automated system to just look at those two and say, hey, this one has got to be the right one. However, I'll leave that there. Suppose there are 3 copies and there's been a change in one of them. How would you identify which one is the one true copy or the 2 true copies? You would say, look, the idea that there's going to be a random change in one of these files, that's pretty unlikely, right? It could happen. Once in a while, it does happen, but it's pretty unlikely. But the idea that the exact change would happen, take this from purple to sand on these 2 images at the same time, that's vanishingly unlikely, right? That's super, super, super unlikely that you would have the same unlikely error in the same place on 2 separate files stored in 2 separate places. So you could reasonably look at that and say, you know what? That one that's different, that's the wrong one. We're going to cast that out. And basically what this is you need a triple copy of any data in some sense. It doesn't necessarily have to be a full triple copy. Parity data has ways to streamline that, but you need, not just 2 copies of the data are not enough to tell the difference. You need a third copy to be able to tell you, one of these things is not like the other 2. And that's basically what parity data does. Okay, so there's bunch of different RAID configurations that combine those techniques in different ways, but basically that's, the last thing I have to say about memory. And it's a good intro to the cloud because it's kind of the same concept of how the cloud works. All right, let's see, we have a little time. We'll knock out a few more slides and we'll leave a little early. Okay, so old-timey hard drives, right, are really slow. They're like a fat little aluminum disc that spins around, and there's a magnetic reader that, drifts across the surface of them and reads what's there. Okay. Now, because that spinning around is physical, there's always a significant time delay, by electrical standards. So there's a few milliseconds for the drive head to reach the right point, and then the disk has to spin around to read it, right? RAM, on the other hand, RAM actions happen super fast. So I'm gonna. Do I not have that anymore? I know I have it. I used to have it. All right, we're gonna find it. We're gonna find it. So online there's a list of latency times, right? So the article is latency times every programmer should know. All right, this one. All right, and it's a little bit old. It's by a guy with the unfortunate name Jay Boner. I don't know him, but I mean, he should have sought a career in porn, I guess, but whatever. Anyway, the idea, just to give an idea what we're talking about. So these numbers are 10 years old, but mostly relative to each other, they're the same, the relative differences. So L1, L2 cache references, those are static RAM, right? And when I say static RAM is blindingly fast, looking something up can be half a nanosecond, right? That's super fast. Ordinary RAM, they have here like 100 nanoseconds, right? Which is 20 to 200 times slower than these other kinds of RAM. So RAM, ordinary synchronous dynamic RAM, sure, it's fast. 100 nanoseconds is fast, but it's not that fast. Other stuff, reading data from a disk, right? So solid state drives were pretty fast. They're faster now, but RAM is still faster. Otherwise, you'd use, and they don't wear out, or ordinary RAM doesn't wear out. The disk seek time around 10 milliseconds, right? Maybe that went down to the range of like 5 milliseconds, but still, rough numbers, 10 milliseconds versus, let's say 100 nanoseconds, right? It's almost like a million times faster, right? It's like, you could figure out the numbers. It is like millions of times. This is millions of times faster than disk. So anyway, Facebook had this basic problem of, yeah, disks are cheap, right? So like these days, for example, a terabyte disk drive maybe costs about $50 depending on quality. 8 gigs of RAM, again, depending on which generation you're using and other attributes, costs a comparable amount. 1 terabyte of RAM costs a whole lot more than 1 terabyte of solid state drive. So the basic problem Facebook has is that disk space is really cheap, but it's also relatively slow, right? So they'd like to use RAM for everything because RAM is super fast and it also doesn't wear out, but right, you don't have enough money to use RAM everywhere. You don't have enough RAM to have exabytes of it. That would cost a whole lot of money. So what do? Well, you try to figure out where it makes sense to use RAM. So stuff that needs to be fast, that's where you spend your RAM money. Other stuff that doesn't need to be so fast, you use disk. So the basic case for that is this kind of hybrid system, right? So the couple slides I have here talk about this stuff. So I'm just going to draw a picture. Then I guess this will be a good time we can come back and talk about it on Tuesday. So the basic problem that Facebook is dealing with. So you have, users on one side, and the users are going to send requests to the Facebook system. Now, Facebook would like to put everything in RAM. So that's not, it can't, right? But I'm going to say popular data goes here, right? Because it's more likely to be requested. Everything goes here in disk. So I'll say here disk. All data, including backups of any popular data, right? So literally all the data that the organization has, like for Facebook, all their images, every image is going to be stored on disk somewhere. So the way this works, if a request comes in, hopefully it's stored in RAM, right? If it is, then RAM can say, yup, here you go. And that was super fast, right? That just took a few milliseconds to deliver that, to find and deliver that. But if it's not in RAM, then the request gets forwarded to disk, where the picture is going to be. That's going to take longer, but eventually it will get back, right? So the second part of this, though, this would be fine if this is how the system was and it stayed static like this and nothing ever changed. Then Facebook could say, okay, yeah, all the stuff in RAM, is the popular stuff. All the stuff on disk is the not so popular stuff. But Facebook has this additional problem of what's called churn, right? Basically, today's popular data is tomorrow's forgotten data, right? Once something is done, probably there's a pretty good chance nobody's going to look at it for a long time. So constantly there's going to be new data going into RAM, pushing out what's already there, and then Facebook has to update the contents. Likewise, every now and then, some old chunk of data might become popular, and Facebook has to manage that. Say, oh, this particular bit of data is popular. We need to cache that here in RAM. So there's this additional layer of management issue. But the basic idea, like all businesses essentially work like this. They pick what they think is an adequate bank of RAM. They put their popular data in it so they can respond to those questions quickly. Everything else, including backup copies of what's in RAM, gets stored in permanent storage, because number one, that's the only place it's stored for unpopular stuff. Even for popular stuff, you don't want to lose it because some intern trips over a power cord, right? Yeah. All right. This seems like a good break point. So I'm just going to say, remember, labs next week. If you can get a copy of I hear the bookstore is out of the lab manual, so I'm going to call up the publishers and try to get some delivered next week. You know, we'll see how that goes. All right. We'll see you next week.